continue to talk about trees. Last time we discussed the problem, LCA problem, when we have a tree and we learn how to find the lowest common ancestor of two given nodes in log n time using binary lifting and also using Euler tour and some data structure to find the minimum on a segment. Today we continue the topic and we discuss one more data structure about trees. And the problem we'll solve is the following. You have some tree, again, let me draw some small tree. So you have some tree and you have some value in each node. And what you want to do is to calculate some function on some path on this tree. So you're given two nodes, node U and node V. And look on the path from U to V. So you look on this path. And try to calculate some function on this path. So each node has some value. So here, another value like A, B, C, and D. And you want to calculate function like A plus B plus C plus D. So this plus is some associative function, like we discussed in the second trees. I have no idea what it must use. Draw a cat in the middle. We'll have a break in the middle and I'll draw a cat if you ask again. Back. So, that's the first question. So again, you need to think this request calc, let's see, calc from U to V. And the result is sum on path from U to V. Cool. We can solve this problem using binary liftings. And we didn't discuss it in the previous lecture, but it was in the home task. So we will discuss it tomorrow when we'll discuss your solutions for the home task. It's actually quite simple. When you learn how to use binary liftings, you can not only find the lowest common ancestor, but also to calculate some function on this path. It's not very hard, so we will discuss tomorrow. And I really expect some of you to solve all these problems, so we'll have something to discuss. So if you have only these requests, then you can use just binary liftings, and using these binary liftings calculate any function on any path. But what happens if the tree changes? So if you have another request which changes the value in the node, let's say set Vx set value of node V to X. So we'll have two requests. First request will change the value in some node, and second request will calculate some function on a path in this tree. So that's the plan. Okay, is it clear? Let's go. So before we start to solve this problem on a tree, let's try to solve this problem on some special cases. So that's usually one of the first things you need to do when you have some problem. So when you have some task and you want to solve it, let's try to first solve some special cases of this problem and see if we can solve these special cases. If we cannot solve these special cases, then we obviously can solve the whole problem, right? So the simplest case of the tree is a bamboo tree. So if you have a tree like this, that's obviously a tree. So let's first try to solve our problem on this tree. So if we have a tree like this, and we have these two requests. So first request changes the value in some node, and second request calculates some function on a path in this tree. So you have some nodes U and V, and you need to calculate your function on this path. What data structure can we use? The It turns out it is quite familiar, this section. So we already see this data structure, and we already see this problem in some previous lecture. So in some of previous lectures, we actually have exactly the same problem. So what data structure is it? Again, you have two different queries. First query is to take some node and change the value. And second query is to take two nodes and calculate some function on this path. Yes, you can take segment tree. That's obviously a segment tree. This tree is just an array of nodes. Yeah, so you need to change the value in one element of your array, and you need to calculate function on some segment of your array. So you just use segment tree to solve this problem, and that's all. And now let's go back to the tree. No, first, if you see that you need segment tree in this simple case, you obviously need at least something that complicated to solve the problem on a whole, on a regular tree. Yeah? No, because even for this simple case, you need segment tree. So for this case, you need maybe something even more complicated, right? Cool. So how will solve this problem? We'll solve this problem in a very simple way. We will try to split our tree into some paths, and when we'll use these segment trees to calculate function on each path, and when they will combine all these results to get the whole result of the function on this given segment. That's roughly the theme we have today. So the technique we'll discuss is called heavy light decomposition. How it's working? Let's draw another tree. I just like to draw trees. So let's have some tree. Something here, and here, and something more. And maybe something here, and something again here, and something more here. Let's have some big tree. Yeah, good enough. So let's have some nice tree. Now, what we'll do? We'll look at all edges on this tree, and we'll split these edges into two classes. We'll have heavy edges and light edges. How to say if the edges are light or heavy? Let's see. We'll look at each node. Look at child of these nodes, all children of these nodes. So each node has some children. Now for each child, we'll calculate the total number of nodes in this subtree. So below each child, there is some subtree. Some subtree here, some subtree here, some subtree here, some subtree here, some subtree here. We'll look at all these subtrees and find the largest subtree. Largest is just by number of nodes. So we'll calculate the number of nodes in each subtree and find the largest one. And that's all. And then we will mark this edge as heavy edge. So this one edge will be the heavy edge. That's all, that's the whole plan. So for each node, we'll do the following. We'll calculate the size of all subtrees of its children, and then take the largest one and say that this edge, the edge to the largest child, is the heavy edge. Well, let's try to mark all the heavy edges in this picture. Yeah, there's another way. There are two schools of heavy light decomposition. Okay? First school is like this. Another way to define the heavy light decomposition, maybe you see it in other lectures, is to say that the child is heavy if, so the size of this is x. So say that child is heavy, its size is at least half of the all elements in this tree. In this definition, some node may have no heavy children. So for some node, there might be no heavy children at all. And if you have any heavy child, then you have only one heavy child. That's basically all the properties we need. This also works. This also works. That's just an alternative way to think about heavy-light decomposition. Sometimes it's more comfortable to do it like this. In most cases, in practice, it's more comfortable to do it like this. Just do not to think about this. This property is cool, but this is much easier to check and easier to how to say, to implement. So this definition also works, but I will use this definition just because it's more comfortable for me. Okay. Both definitions will give you the same asymptotics. This is actually a little bit faster because you kind of want to have many heavy edges. The more heavy edges you have, the faster your data structure will be. So if for some node you have no heavy edges, so like if you have this node, the size of both these children is less than half, because the size of this is 3, size of this is 1 and 1. So 1 is less than 3. Then you have no heavy children. And you kind of want to have as many heavy children as possible. No, because the heavy edges will be just we will calculate it faster than light edges, something like that. So I will use this definition of heavy edges. This also works, but it's kind of slightly slower. So I won't do this. Okay, let's go back. So we'll take our tree and we will mark all the heavy edges. Do it recursively. We don't do recursion here. You need recursion to like iterate over all nodes of your tree and to calculate all the sizes. Can you call them heavy? No, I have only one heavy child. It is the heaviest child. There's always, if the node is not a leaf, then there is exactly one heavy child. It is the largest subtree of the children. If you have several trees of the same size, you just pick one of them. Say this is the largest. If you have several trees of the same size, just pick one of them. Say this tree is heavy. So there is always exactly one heavy child of each node except of the leaves. Cool. Go back. So we'll take this tree, and first what we need to do is calculate the sizes of all subtrees. Well, you can do it recursively. Yeah, you can call a recursive function which calculates the size of the subtree. So you call recursion. It goes here, here, here. Stops here, so size of this subtree is 1, size of this is 2, it's 1, it's 4, it's 1, it's 2, it's 2 plus 4 to 7, and so on. So you just call a recursive function to calculate the sizes of each subtree. And now you actually can do it in the same recursive procedure. So you can call the same recursive procedure to calculate all the sizes and also to find the largest child. Now, for each node, you find the largest subtree of all children and mark this edge as heavy. So this edge is heavy, this edge is heavy, this edge is heavy, for this is right edge is heavy, and so on. For each node, you take one of the children and say this edge is heavy. This is heavy, this is heavy, this is heavy. No, one of them doesn't matter. For this node, this is heavy, and so on. And you do it not any of them. Left one, right one. For the root, no, left one basically, obviously, right? That's all. Oh, hello everyone, we just started to talk about heavy-light decomposition. That's all. That's the whole plan. Again, you can do it in one recursive call. Well, basically, what you need like, how you do it. So you call this function, let's say go of x. So you take this node x, you calculate the size and then find the largest child. So let's say size equal to 1, then you iterate of all children of x, calculate the size of this, so this is y. Calculate the size of y, let's say c equal to go of y, s plus equals c, so if c greater than best, then best equal to y, equal to c, that's not best, that's the maximum. If c is greater than max, then max equal to c, and heavy of x equal to y. Then return as like this. So it's quite simple recursive procedure. You iterate for all children, calculate the same function. This function returns you the size of the subtree. You add this size to the size of your subtree, and also find the maximal size of the subtree. So this maximal child will be the heavy edge of your node. So for this node x, the heavy edge will be y. So here you find the heavy edge of node x. And also in the end you return the size of your subtree. It's quite simple, right? Good? That's all. And you can, the cool thing that you can do it in linear time. So this recursive procedure is actually linear, works in linear time. So total time of this procedure will be n. So in linear time, we can split all the tree into some. You can split all the edges into light edges and heavy edges. Cool. Now, let's look at these heavy edges. So let's go only at the heavy edges. These heavy edges form some paths. Well, obviously, because each node have only one heavy edge to the child, then these heavy edges form some from some paths. So if you start from some heavy edge and try to go down, you go down here. Then you have only one heavy edge, so you take this heavy edge, then you take this heavy edge, and so on. So you will walk to some heavy path. So the whole tree will be split into some heavy paths. Let's draw this path. So you have this heavy path. You have this small heavy path, this small heavy path, this heavy path, and this one. And also this one, and this one, and this one. Oh, no, not here. This one. Like this. So you have some heavy paths. Also, you have some single vertices like this. We'll say that every vertex like this, which is leaf and doesn't have any heavy edge. We'll just say that it's a heavy path of size 1, so it's heavy path of single vertex. So this is small heavy paths. That's all. Now we just split all the nodes of our tree into some paths. That was the plan. That's all. That's how you make heavy light decomposition. Now, let's go back to the function, so to these requests. How will we calculate these requests? So imagine you have two nodes. You have some node. Oh, let's take, for example, this node. So this is node U, and let's say this is node V. and you try to calculate function on a path from here to here. How will you do it? Let's see. Let's look on the path from U to V. This path consists of some segments of heavy paths. So we start from here. We need to take this whole heavy path. So we take this whole heavy path. Now we go to here, and from here we need to go up to the root. So we need to take this segment of this long heavy path. So we need to travel there up to the root. Now we go here. I need to go to this V. So we go here, use this segment of this heavy path, then go here, take this node, and take this node. Like this. Yeah. It's not that clear because I just used too many hatchings here. So this very bold hatching is the nodes we travel when we move from U to V. So this is V. So again, when we travel from U to V, we visited all these nodes. These nodes form some segments of these heavy paths. Can we just combine the light each heavy path with one light edge about? Okay. But why? I want to split nodes, not edges. You can, if you want to split edges, you can add this last edge to your heavy path. That's right. But I want to split nodes, not edges. So I don't need to split edges. I have no idea. It's from the World Finals in Phuket in 2016. It was a long time ago. We make these t-shirts. I believe it's something from Indian mythology. No idea. I'm not that good in... Cool. So, what next? What next? Let's try to calculate the number of different heavy paths we visited when we travel from here to here. So let's look on some path from U to V. It turns out that the number of different heavy paths is pretty small. How to prove this? Let's look on the path from U to V. Again, let's split this path into two parts. When we travel from U to V, we travel from U to this LCA. So this node is LCA of U and V. So we travel from U to LCA, then from LCA to V. So let's look on the number of different heavy paths on the path from U to LC. To do this, we'll calculate the number of heavy paths from U to the root of the tree. So let's look on some node U and look on this path from U to the root of the tree. And let's calculate the number of different light edges on this path. Well, it turns out this number is pretty small. Why this number is small? Because each time you take this light edge, it means there is another edge which is heavy edge. So when you start from this node and go to the root, let's say if this node is heavy, but this node is light. So you take some segment of the heavy path and then you have this light edge. When you have the light edge, it means that for this node there is another edge which is heavy. So this edge is heavy. If this edge is heavy, it means that the size of this subtree is greater than the size of your subtree. So if you take this subtree, and your subtree. If your subtree has size x, then the size of this heavy subtree is greater or equal to x. And it means that the size of your parent of this node, of this size of this tree, is at least 2x. Right? So again, you go from u to the root. If you see some light edge, it means that you move from subtree of size x to subtree of size at least twice. Yeah. So the size of this subtree is at least twice bigger than the size of this subtree. That's all. Now just look on the sizes of this subtree. So size of this root is n, and size of this u is 1, is at least 1. Yeah? So you start from the tree of size at least 1, and each time you see a light edge, you increase your current size twice. In the end, you must have a size n. So you cannot increase your size twice more than log n times. Okay? So number of light edge cannot be more than log n. Clear enough? So again, why is it log n? Because each time you see a light edge, let's go here. Each time you see a light edge, it means there is another subtree, and size of this subtree is at least as big as the size of your subtree. So when you go from here to here, you go to this tree of size at least twice bigger than yours. And you cannot do it more than log n times. Like in this, you're right? We have this almost the same explanation when it's discussed joint set union. Here is a little bit. Here's a little bit more interesting. So if you start from vertex V, you take here, size of this tree is. So here your size is 1. Now you see this light edge. The size is 3, so it's at least twice bigger. Now you go here. The size of this size tree is 4, 5, 6, 7, 8, 9, 10. So again, when you move from here to here, the size is increased at least twice. Then you go here, here, here. So here size when you take heavy edge, your size is not decreasing. So the size of this subtree is at least 10. No, actually it's more than 10. It's 10, 1, 2, 3, it's 13. Now when you move from here to here, this size of this subtree is at least 28, 26. I'm not sure. It should be bigger, but not a big deal. So again, every time you see a light edge, you increase your size twice. You cannot do it more than log n times. So the total number of light edge on your path is no more than log n. Good. Now, how it will help us to calculate the number of heavy paths? No, it's quite simple. So if you look on the light edges, these light edges are simply the border between two segments of different heavy paths. So if you look on the path from u to the root, you have these light edges, and all other edges are heavy. So this you have this path. Some edges are light, some edges are heavy. So you have some heavy edges. They form some segments of your heavy paths, like this. And if you have no more than log n light edges, then these log n light edges will split your path into segments into no more than log n segments. So each of these, so you have no more than log n segments of different heavy paths. Do you have any bounds on number of decomposed paths in general? I don't get your question. So if you split your tree somehow, not in heavy light style, but just split your tree into segments in some way, you may have many trees new. So if you use some decomposition into paths, not heavy light decomposition, you may have more segments in the path from U to V. I'll put it in the home task. So it's important that we used this heavy light style to decompose our tree, because we used if the edge is slight, then there is another heavy edge, so this size increased twice. Yes, no. Yeah. Actually, what we need is to calculate number of paths from U to V, right? So paths from U to V. But if you look on path from U to V, then you go from U to this LCA. On this segment, you have no more than log n different heavy paths. And also on this part of this path, you have no more than log n different paths. So you start from U, go to LCA, and then go to V. Yeah. So here you have up to log n heavy paths, and here you have up to log n heavy paths. So total number of these paths will be up to 2 log n. So on this path from U to V, you have up to 2 log n heavy paths, right? Well, these heavy paths are actually not like this. So you have some segments of heavy paths. So this U is something like this. So you have some heavy path here, you have some heavy path like this, you have heavy path like this. So that's basically how the situation looks like. You start from node U, and you need to take this segment of this heavy path. Now we take this segment of this heavy path, this segment of this heavy path, something like this. Cool? Okay. And that's almost all. Now, how to calculate the function? To calculate the function, we simply need to calculate the function on these segments. So we'll calculate function on each segment, and then calculate the sum of all these sums to get the total sum on this path. So to calculate sum on each segment, we will simply use a segment tree. So we will use this technique. So for each heavy path, we will build a segment tree. This segment tree will give us the sum on any segment of this path. Let's write it here. For each path. So for each path, we will build a segment tree. The number of segment trees will be up to n. Yeah. So you may have up to n segment trees, but the total size of these segment trees, total size of these segment trees will be linear, because each node belongs to one of these segment trees. So the total size of all these segment trees will be linear. And now when you calculate the function from U to V, what you do is just to split again. You find this LCA, you know how to find LCA. So you find this LCA, you take this path, calculate the function on both these paths. How to calculate function? You start from node U and try to go to LCA. You take your current heavy path, look on the top node in this path. If this node is below LCA, then you take this whole segment and go to the parent. If this top node is above the LCA, then you let me just write it here. So what happens? So you have this node U. This is your LCA. You take this node U. Look on the heavy path which contains node U. You can make for each node you can remember the pointer to the segment tree. Let's know how it should be implemented. By the way, I just explain what's going on. I will later explain how to implement it to make it much less painful. It can be implemented very easy way like this. So this function is pretty easy, right? So all this data structure can be implemented quite easy. I will explain it a little bit later, but let's just try to understand what's going on before. I will try to explain what's going on, and then we'll go to very simple implementation of this. Let's go. So we take this node U. This node U belongs to some segment, or to some heavy path. Let's take the top node of this heavy path. If this node is below the LCA, then we just take the whole segment of this heavy path from here to here. Add this sum to the result, and then move here. Then again, we take this node, find the heavy path which contains this node, take the top node on this heavy path, see it is below LCA, so we take this sum, add the sum to the result, and so on. At some point, we'll take the heavy path like this, and the top node of this heavy path will be above the LCA. So then this node is above the LCA. We just take all the nodes from the U to LCA. So we take the sum on this segment, and that's all. So it's quite simple code actually. We start from node U, take the top node of this heavy path, see if it is below LCA, we add it to the result and go here. If it is above the LCA, then we take the sum to the LCA, and that's all. So it's simple while. It's actually quite simple. Cool. That's all. That's all. So you calculate this sum from U to LCA, calculate the same sum from V to LCA. Now you just add one sum to another and take the whole sum on this path from U to V. That's all. What will be the total time complexity? Let's see. So what is total time complexity? We start from node U and go to LCA. On this way, we will visit up to log n different heavy paths. So on each heavy path, we need to make these requests. Each of these requests is just a request to the segment tree. A request to the segment tree costs you log n time, right? So each of these requests costs you log n time. So we need to make up to log n requests. Each request costs you log n time. So total time complexity will be log squared. That's all. And how to update values? So we need to make two requests, right? First request is calculate the function. Second is to update the value in while node. No, update is pretty simple. So when you need to update your value in some node, so you take some node, so you take node V, and you want to update value here. How to update the value? No, you take this segment tree. The segment tree corresponds to this heavy path. So you take this node V, you take this heavy path. You have some segment tree assigned to this heavy path. So you take this heavy path, take this segment tree, and update a value in this position. That's all. So update costs you log n time actually. So this is the calc function, and you have log n time for the set function. Now, you can do it even faster actually, and on the next lecture we'll discuss how to make this even faster. So you can use the technique which is linked tree, and the next lecture we will discuss linked trees. In linked trees you can calculate function in log n time amortized. So linked trees work in log n amortized time, and it actually allows you to do even more operations. So in linked tree you can not only calculate this on a static tree, but you can modify your tree. So you can cut the branches of your tree and link them in other positions and so on. So next lecture we'll discuss much more sophisticated structure, which will allow you to modify your tree as well. So this structure is fixed for your tree, right? If you change your tree, you need to rebuild the whole data structure. But in linear tree, it can adapt to the changes. When you change your tree, it will adapt and rebalance itself to match your current state of the tree. And also it will work in log n time for this calculator. We'll discuss it on next week. Cool. And now I want to spend some time to discuss how to implement it, because it's kind of look painful to implement this, but it's actually not. It can be implemented quite easy way. So, especially some of you came from code forces, so you may be interested about how to implement this in the context. So it's quite easy data structure. So what is the easiest way to implement this data structure? Let's see. What I will do first, I will use not many small segment trees, but one big segment tree. So instead of having many small segment trees, it's just complicated. Yes, if you have small segment trees, it basically means that you need some data structure. You need to make some structure segment tree, make array of this data structure, make pointers from node to the corresponding segment tree, and so on. It's just complicated. So instead of doing this, I will use only one big segment tree. How to do it? I need to draw another tree. Sorry. Let's have some tree. I need some labels for the nodes. So I need node 1, node 2, 3, let's say 4, 5, 6, 7, 8. No? Let's have 9, 10, 11. I need to stop at some point. Okay, that's good enough. So now, what I want to do, I want to iterate this tree in such a way that first I iterate the heavy subtree and then all other subtrees. So I already marked the heavy subtrees for each node. So let's do it. So for each node, I know the heavy subtree of this node. So this tree, any of these, let's say this. Now for each node, I know the heavy subtree of this node. And now I will simply, again, I make a recursive traversal of this tree. But in this recursive procedure, I first make recursive call for the heavy node, and then recursive calls for all other nodes. So I start from the root. It's not 1. Then I call the same function for the heavy subtree. Heavy subtree is this. So I call recursive function for this node 2. So I go to node 2. And then from here I go to the heavy subtree 7. Then go to the 8. Then go back here. Now I recursively visit all other subtrees except the heavy subtree. So I also have this subtree 4. So I go this subtree 4. Let's go another. Yeah, just to make it more interesting. Now for this node 4, I go here. I go 12. Then go back. Now I started from root and visited the heavy subtree. So now I just visit all other subtrees recursively. So I take these two subtrees and visit both of them. So I go to here to subtree 3. So I visit subtree 3 and then go to 6, then go back. And then go to this subtree, go to subtree 5. Here I visit 9, 11, then back and then 10. That's all. Now, let's look on this sequence. So again, you can calculate this sequence in very simple recursive procedure, right? Oh, let me try to go. So let's relay P. So it's go 2 of X. Okay. I'm not very creative today. So this, how you do it? You first iterate over the heavy subtree. You make. So if children is if children. So first you put your node in P. Then if is not empty, not empty. Then first you recursively iterate into your heavy subtree, and then iterate over all other subtrees. Let's say if y is not heavy, we call something like this. Okay, this simple recursive reversal of the tree, but it's just modified to first go to this heavy subtree and then to all other subtrees. You get this sequence of nodes. Now let's see, in this sequence of nodes, how these heavy paths are laid out. So if you look on each heavy path, this heavy path forms some segment of this sequence. So first you have this 1, 2, 7, 4, 7, 8. It is some heavy path. So you have heavy path 1, 2, 7, 8. Yeah, it corresponds to this to this heavy path. Now you go to vertex 4, you have this heavy path 4, 12, so you have this heavy path. Now you go to node 3, you take this heavy path, 3, 6 is another heavy path. Now 5, 9, 11 is another heavy path, and in the end you have this heavy path of one node. So every heavy path is a segment of this sequence. Yeah? You stop saying everything is fine. So again, I just want to make the simplest implementation of this data structure, right? So in theory, you can do all this stuff. You can split, make these small segment trees, and so on. You will get this time complexity. That's fine. I just want to make the simplest implementation for you to use in the contest. Don't waste some time. It depends. Actually, we don't. So the total size of all these small segment trees is also linear. So the total number of nodes in these small subtrees and in this one big subtrees will be the same. So you have if you have tree of n elements, you need up to 2n nodes in total, right? So if you have segment tree of size n, then you need something like n. So if you have n leaves, you need n more nodes here to make the segment tree, right? So the total number of nodes in the segment tree is like 2n. So total size of this small subtree of these trees will be 2n, and total size of this big tree will be 2n. You may lose something when you make these recursive, when you make these calls. You make, like, if you use these small subtrees, it will be logarithm of size of this path, and here every request will be logarithm of n. But you can make the segment tree from bottom to top. If you make segment tree from bottom to top, then every request will cost you the logarithm of the size of your request. So it's the same time complexity. So actually, no, you don't lose anything here, because you just make it much more simple actually. And the time complexity will be the same, and the constant factor actually will be less. But because you don't have all these small arrays, you have only one big array. So it's much simpler. That's all. Now, how to use this? You use this very simple way. You take each node. So when you want to calculate sum on a path in the heavy path, or sum on a path in the heavy path, sum on segment in the heavy path. So you have some heavy path, and you want to calculate sum on some segment of this path. So you want to calculate sum from this 2 to this 8. You just take nodes 2 and 8, find them in this sequence. So here we have 2 and 8. And just calculate sum between these nodes in this big segment tree. So you don't need to remember which node corresponds to which heavy path. You just take these two nodes, find them in this sequence. Well, basically, you need to find index for each node in this sequence and calculate the sum between these two indices. And this will be the sum on the segment of corresponding heavy path. Now, what next will be simplified? I want to simplify this LCA because, like, what you can do, you can use the binary liftings or other methods to find this LCA, but you actually you don't need to. You can use this heavy light decomposition to calculate this LCA as well, and just do it on the fly. You don't need any special code to calculate this LCA. You can calculate this LCA just using your heavy light decomposition. How to do it? Let's do it like this. What's the plan? What's the plan? And you have two nodes. You have node U and node V. Let's look on the segment on the heavy paths which contains node U and node V. Each heavy path can be simply associated to the top node of this. So for each node, let's make a pointer to the top node of the corresponding heavy path. So from each node, let's have a pointer to the top node of the corresponding heavy path. So all these nodes have pointer to here, all these nodes have pointers to here, all these nodes have pointers to here, and this pointer to itself. So for each node, let's calculate the pointer to the top node of the corresponding heavy path. We can do it in the same recursive procedure. I will just not do it. You can do it right here. When you build these heavy paths, you can also pre-calculate these links. Or you can make another recursive procedure, as you wish. It's quite simple. So each node must know the top node of the corresponding heavy path. So if you have some heavy path, what I want to do is to have pointer to the top node of this heavy path. So all nodes of the heavy path have pointer to the top node of this heavy path and it itself. So it will be top of X. So top of X is the top node of the heavy path contains node X. Now, the algorithm. So you take these two nodes and you want to calculate the function on this path. Let's find two heavy paths which contains these two nodes. So we have one heavy path contains node U and another heavy path contains node V. Let's take these two top nodes, let's say X and Y. Heavy node? No, you have not heavy node, you have heavy edges. So every node has one of the edges is heavy. It corresponds to the heaviest child of this node. And these heavy edges split all your tree into some paths. So you have these heavy paths. And for every heavy path, I have a pointer to the top node of this heavy path. Now, the algorithm. So we start from node U and node V. For each of these nodes, we know the top node of this heavy path. So for node U, we know the top node is X. For node V, top node is V. I'll just write the code. So X is the top node of U, and Y is the top node of V. Now, first, if these nodes are the same, so if X equals to Y, what does it mean? It means that U and V belongs to the same segment tree, right? It belongs to the same heavy path, right? So if X and Y is the same, it means that you have situation like this. You have, let me write here. So we have U and V somewhere here. So you try to find the top node of this heavy path and go to the same node here. So this node is X equal to Y. So if U and V belongs to the same heavy path, then you just calculate the sum on this on this segment. So you take this segment from U to V, calculate the sum, and that's the result. So we add to the result sum from U to V. So this is called to the segment tree. So you take this segment tree, find U and V, calculate this sum. So this is the call to the segment tree. And that's all. If X and Y are different, then what we'll do? We'll take the depth of these two nodes. So we'll take depth of X and depth of Y. Depth is distance from the root. So let's look on the distance from the root to X and from the root to Y. And take the deepest one. So for example, if depth of X is greater than depth of Y, then I claim that LCA is above node X. So all these nodes below X are not LCA of U and V. So the path from U to V contains all the nodes from U to X. So I can take all these nodes on this path and just add them to the result. Now, why it is true? No, because if Y is above, it means all nodes from X and below are different. So if you take path from V to LCA and from U to LCA, right? So somewhere here is LCA. So your path contains of this path and this path. And all nodes from X and below are different on these paths. Well, because here you have Y, and on this level you have different parents. It means on this level you have all parents from this level and below are different. It means that all these nodes belong to the this half of this path from U to V, right? Clear enough? So if you take deepest of these two nodes, and then you can add all these nodes on this path to your result. So you just add the sum from U to X to the result. And move the node U. So you added these nodes to the result. So now you can move U to this position. That's all. We move U as a parent of X here. That's all. Now you continue. So now again, you have node U and node V. You calculate the top nodes of each heavy path. So you take this heavy path and this heavy path. So this node is X, This node is y. Again, you calculate the depth of these two nodes. Take the deepest one. Now here, y is deeper than x. So depth of y is bigger than depth of x, right? So if y is bigger, then you take all these nodes and add all these nodes to your result. So else you add from y to v to your result. No, actually, if you I just say sum and plus because I calculate sum. If you have some associative function, you actually need to take care about the orientation of your, like the direction of your path. So if you have some associative function, it's not always commutative. Yeah. So if you take path from u to v, it goes like this. First it goes up, and then it goes down. So when you calculate function, so on this part you need to calculate function from bottom to top, and on this part you need to calculate function from top to bottom. So for different associative function, it may be different, right? So you actually need to calculate two different segment trees for function like this and for function like this. So these two parts should be calculated separately, actually. So you just need two segment trees. One segment tree to calculate the left branch, another segment tree to calculate the right branch. Yeah. Just small details. If your function is commutative, it doesn't matter. Yeah. If you have minimum sum or something else, it doesn't matter. If you have something strange, which is not commutative, like matrix multiplication, something like that, then you need two separate segment trees, one to calculate left branch, another to calculate right branch. That's life. So you add this to the result and then move v. Let's move here. So you add this to the result and move v. Then at some point, this u and v will belong to the same. That's why I'll choose here. That's the whole code. So at some point, u and v will belong to the same heavy path. Then we belong to the same heavy path. Then this condition will be satisfied. So you go into this if, and you just add this result, add this sum from u to v to the result, and return. That's all. So that's basically the whole code of the heavy light decomposition. It's not that that scary. So if you have the segment tree, but you should have segment tree in your inventory, right? So if you already have your segment tree, then that's basically the whole code you need to add. So you need some code to split your tree into segments. You need some code to make this sequence. And now, based on this sequence, you build your segment tree. And that's the whole code basically to calculate the function on a path. Here you make two calls to your segment tree. And that's all. So it's not that scary. It's quite simple data structure, actually. We'll discuss much more complicated data structures later.